Part 3 of two-dimensional motion, other projectiles. So projectiles that are not what we call horizontal projectiles. Projectiles where the original velocity is not just x velocity, but there's a y component as well. This diagram shows what happens to the velocity of the projectile as well as to the two components of the velocity. Look at the x component, this little green arrow here. The x component is constant. You see the whole time the x component stays the same. So regardless of where you are in the problem, the x component is the same. Let's look at the peak of the path. We have thrown things straight up into the air and had them come straight back down before. And we've dealt with these problems, and we've been able to find the time it takes to reach the peak and how high it goes. And one question that we asked a lot was, what's the velocity at the peak of the path? And when an object is thrown vertically upward, the velocity at the peak is 0. That means Vy is 0 at the peak. Well, if you have a projectile that's not just going straight up, but that has some horizontal velocity, if Vy equals 0 at the peak, that means at the peak, the velocity is equal to the x component of the velocity. Okay, so this is where it's moving the slowest, because it doesn't have any y component. But it doesn't have a velocity of 0 anymore because there's a horizontal component that doesn't change. Also notice the original velocity, V0, well, not the red one, the blue one, the actual velocity. The velocity at the beginning is the same as the velocity at the end. V equals V0. Now the direction is different. So this one is moving, at a large angle with respect to the x-axis, and this is moving with an angle that's still a large angle with the x-axis, but it's not moving up and to the right, it's moving down and to the right because the vertical component is negative where the vertical component here was positive. But the magnitude of the velocities is the same. The velocity at the beginning, the speed at the beginning is the speed at the end, and the speed in the middle is just the x component. Okay, let's learn some more stuff about other projectiles. We're still going to have to divide the problem into vertical and horizontal parts. So we're going to have to use the very first thing that we learned about finding the components of vectors. We're going to have to be able to find the components of an original velocity, of an initial velocity. Notice, as I said, the x component of the velocity still remains constant. That green arrow is the same size all the way through the problem. Also notice that the y component gets smaller. Look at the red. Well, it makes sense. If you throw a ball straight up into the air, it goes slower and slower until it has a velocity of 0, and then it speeds up as it falls. So the y component gets smaller, goes to 0 at the peak, and then gets larger, but the sign is changed. Positive velocity until the peak, the y component becomes negative after the peak. And the velocity at the peak of the path, the velocity is the x component because the y component is 0 at the peak. Now these are those little questions that you can be asked on a quiz or a test, not problems that you have to solve, but things that you have to know. So make sure that you take good notes about this stuff. And again, like I said before, the final velocity, V final equals V initial. Now those are not components. That's the actual velocity with which it's moving. There is a sign, a direction difference. It'll be moving upward at the beginning and it'll be moving downward at the end, but the magnitudes of the velocity at the end and the beginning are the same. Same equations. Horizontally, Vx is x over t. And we'll have to rearrange that sometimes to say x is Vxt. But they're the same equation. So it's not two equations to know, just one equation to be able to manipulate. Vertically, y equals y0 plus Vy0t plus 1/2 gt squared. Pay attention to the sign that you use for gravitational acceleration. Also, the y velocity at any time is the initial y velocity plus gt. And again, the sign on g, you're going to have to think about what sign to put there. And then we may end up using VYF squared. Let me erase that, make it a little bit neater. The final y velocity squared equals the initial y velocity squared plus 2gy. And again, think about the sign that you use for g. Okay, now that we have our toolbox, let's tackle some problems. A kicker kicks a football with an initial speed of 20 meters per second at a 30-degree angle. So you have a kicker, and here's the ball. And when he kicks that ball, the velocity can be represented by the vector that has a 30-degree angle with the x-axis, and the magnitude of the velocity is 20 meters per second. So the first thing that we need to do is find the components of the initial velocity. You have your equations for the components. Remember that the x component is the velocity times the cosine of the angle, and the y component is the velocity times the sine of the angle. Let me get my calculator out. Sorry for the minutes delay. Okay, so Vx is going to be 20 times the cosine of 30, and Vy is going to be 20 times the sine of 30. The cosine of 30 is 0.866, so that's going to be 20 times 0.866, and the sine of 20 is 0.5, so that'll be 20 times 0.5. So I get 17, I'm going to round it to one decimal place, 17.3 meters per second for my x component, and 10 meters per second for my y component. Okay, things that we can find. We can find how long it's in the air. Remember, that's hang time. We can find the maximum height, and we can find the range, or the horizontal distance. And we can find out how fast it's moving any time during the problem. So let's look at how long it's in the air. If I have a projectile, and it goes up to a peak, and it comes down, the y value is 0 at the beginning and at the end. So if we look at our equation, the big one, y equals y0 plus vy0t plus 1/2 gt squared. These two things are 0, so we get 0 equals vy0t. Well, the initial y velocity is 10 meters per second, 10t. Now, this was positive, g is negative. This was up, g is down. So minus 1/2 g, I'm going to just use 10. Math is easier. So half of 10 is 5 t squared. If I move one term to the other side, I get a 5 t squared equals 10t. You see that I can divide both sides by t? Actually, I can divide both sides by 5t. And I get, on this side, just a t. And on this side, I get a 2. So it's 2 seconds for the whole trip. That'd be up and down. So how long did it take just to get to the peak of its path? Well, if it took 2 seconds for the whole time to get to the peak, it only took 1 second. And we may need to use that. Actually, in the next part, it would be easiest if we do. How high does it go? Well, we can use that same equation. Y equals y0 plus vy0t plus 1/2 gt squared. Remember I said it takes 1 second to get to the peak? So what I really want to find out is where is it at 1 second. So y equals, the initial y position is 0. The initial y velocity is 10. We're curious about where it is at 1 second. This is going to be negative because up is positive and g is down. So minus 1/2 times g times 1 squared. So y equals 0 plus 10 minus 1/2 of 10 is 5, and 1 squared is 1, so 10 minus 5 equals 5 meters. Pretty simple. I know this equation looks long. It has a lot of parts, but it's really quite easy to use. How far down the field does it go? How far down the field? That's horizontal. The only equation we have is x equals vxt. Distance is velocity times time. And so the x component of the velocity is 17.3 meters per second. The time for the whole trip is 2 seconds. And 17.3 times 2 is 34.6 meters. And how fast is it moving at the peak of the path? You don't have to do any calculation for this, actually. You do, but you've already done it. Remember, at the peak, the y component is 0. The velocity is the x component, which is 17.3 meters per second that we found way back up here at the beginning. So that's not so bad. It's got a lot of parts. There are a lot of different things that you can be asked about non-horizontal projectile problems. But if you remember all your equations and you take good notes so that you can use this as a template, then you're going to learn how to do it, and it'll be not a difficult thing. A couple other things I want to mention about non-horizontal projectiles. Projectiles that look like this, where both y, the initial y and the ending y are the same. The longest range is gotten using a 45-degree angle. If you use a higher angle than that, the object will go higher, but because the x component of the velocity is less, it won't go as far during that time. If you use a lower angle than that, its x component will be faster, but it won't spend as much time in the air, and so it won't go as far. It's also important to note that pairs of angles will give you the same range. Do you see here that 30 degrees and 60 degrees each give you this range, and 75 and 15 each give you the same range. The pairs of angles that give you the same range are complementary. Remember, that means they add to 90. And so if you know that a 25-degree angle gives you a certain range and you want to know what other angle gives you the same range, well, 25 plus what equals 90? 25 plus 65? And so 25 and 65 would give you the same range.